In chapter 4, we introduced the idea of a probability distribution, and then we studied discrete probability distributions. In chapter 5, we're going to be studying continuous probability distributions, and to study those, we are going to look at these things called normal distributions first. So a normal distribution is a continuous probability distribution for a random variable x with the following properties. First, the mean, median, and mode are all equal. The curve is bell-shaped and symmetric about the mean. So the curve is going to look like this bell-shaped curve here. The total area under the curve equals 1, right? Because it's a probability distribution. The curve approaches but never touches the x-axis as it extends farther from the mean. So in either direction, it gets really, really close to the x-axis, and it gets closer and closer the further you are away from the mean, but it never actually touches the x-axis. And then part 5, between mu minus sigma and mu plus sigma, so essentially one standard deviation away from the mean, the graph curves downwards. So if you think about parabolas, let's say, this looks like an upside down parabola over here. That's what that means by curving downwards. And then to the left of mu minus sigma and to the right of mu plus sigma, the graph curves upwards. So from mu minus sigma to the left, it looks almost like an upwards parabola. This just keeps going down, but to give you a sense, this is opening upwards. And then to the right of mu plus sigma, it's opening upwards as well. The points at which the curve changes from curving upwards to downwards are called the points of inflection. The graph of a normal distribution is called the normal curve. All right, so here's our picture of the normal curve. Notice that it's symmetric around mu, the mean. As you move to the right or to the left, this curve goes down and it gets closer and closer to the x-axis. The points of inflection are one standard deviation below and one standard deviation above the mean. The total area, so even including the stuff that is all the way out to the right or all the way out to the left, when you add up all the area, it equals 1. And with a discrete probability distribution, we can study it using a histogram. With continuous probability distributions, we need to be a little bit more sophisticated with that, and we can use these things called probability density functions. Which sometimes you'll see it shorthanded as PDF. Now, for a normal curve with mean mu and standard deviation sigma, if you were to graph this probability function here, probability density function here, you'd end up getting this bell-shaped normal curve. So it's 1 over sigma times the square root of 2 pi, all times e to the negative x minus mu quantity squared over 2 sigma squared. We're never going to use that in this class, but this is hanging out in the background. And when we get into calculating probabilities, we're essentially having to study this function. Luckily, somebody did a lot of studying for us, and so we just need to understand how to read those charts, not so much how to calculate with this function here. But this is the type of beast that statisticians study. A very special normal curve or distribution that we're going to look at is the standard normal distribution. It's a normal distribution with a mean of 0 and a standard deviation of 1. Right, so it's symmetric around 0 as an area of 1, and each standard deviation is 1 unit. This should look kind of familiar or maybe ring a bell, but the horizontal scale of the graph of the standard normal distribution corresponds to z-scores. So these come back into the picture, these z-scores. So just to do a quick recall, z is equal to the value minus the mean all over the standard deviation, which in shorthand is x minus mu over sigma. And now before we move on to the second page, what we need to do is remove the final 2 pages from this note packet. It should look like a chart like this, where it has z that has all these negative values going down the left-hand side, and then also another chart where you have a z with all these positive values. Remove this, save this. We're going to keep using this chart essentially for the remainder of the entire semester. But in particular, we're going to use it frequently in this chapter.